Oh, tak ngaku dah.
Belum kuat madam because now focus more on mass balance first and other things.
Okay. I sebenarnya you kena one hint that kalau you nak cari semua sama-sama daripada awal, I don't think it's going to finish. So sebenarnya tak tahulah, I do not know macam mana your supervisor give it to you, tapi I kalau dengan student I bahagikan siap-siap. I akan bahagi ada 2 orang buat introduction and something else, I don't know. Katalah market survey. So student A dia jadi ketua untuk proses background. Yang student B jadi penolong dia. Dan student B jadi ketua untuk market demand. Student A jadi penolong kepada market demand. Macam tu I bagi. So kalau you kata you nak cari semua sekali sama-sama, you takkan sempat siap. HISIS will take a very long time to converge. So once you have actually dah dapat kan, you dah decide on what plan, what pattern that you want to use, then pattern usually on the process flow yang very general, but the detail will be given dekat reaction. So the rest tu lah macam I cakap tadi, semua guesswork lah lepas tu. So once you have decided that, you should assign someone, 2 orang to do HISIS. I think my group hari tu I assign, so the pair will have to do HISIS dengan energy balance. Sebab mass balance is quite simple actually. In out je. Energy balance calculation ni susah. So seorang tu jadi ketua untuk HISIS, dia tolong buat energy balance sebab once dia tukar the process flow, energy balance akan go crazy. So dia akan bagi tahu immediately kat kawan dia lah, ataupun when you do it together, I'm sure they are aware there's a change. And so orang yang buat HISIS tu would be the second wingman lah kiranya untuk orang yang buat energy balance. So I selalunya I pairkan macam itu, because kalau you nak buat, let's do it together, everybody buat proses background sama-sama, memang tak sempat lah. Minggu 12 nak kena hantar kan. So you have to bahagikan kerja wisely. Kena fikirlah. Sekarang dah minggu berapa ni? Minggu 4 ni, 5. So you have another 7 weeks. 7 weeks tak masuk lagi dengan minggu assessment, tak masuk dengan final year project yang you kena settlekan. So this semester is a testing semester. You nak gaduh ke nak apa masa ni lah. Right. Tak ada soalan dah? Kenyap Okay, if tak ada soalan, I akan present. Let's go through this. Boleh nampak tak app ni screen?
Boleh madam.
Nampak doktor.
Right, okay. Now, so kalau kita tengok sekarang ni apa yang I buat, so this is the one that we have done untuk lab 4 hari tu. So this is actually the example of distillation column yang I berjaya optimizekan. So this is out of tubular plug flow reactor. I think the conversion is 40%, and then we put in a compressor in here, and then this was the operation is at vacuum 0.5 bar. Okay, this one vacuum 0.5 bar, this one also 0.5 bar, this one is 1.8 bar. So that's why I have to put in expander dekat sini, because I want to reduce the pressure. Okay, so this is 7 bar, so I want to reduce the pressure. I put in down to 3.5 bar. So when you put in valve, you make sure there's no condensation happen. But then kenapa ya, I pun tak ingat kenapa I letak expander. But then if you notice, your expander ni will be at the expense of some temperature change. So katalah temperature masuk ni 760, yang keluar daripada expander 720, dia ada 40 degree Celsius change. But if you can afford to lose that kind of temperature, then okay, you can put expander. If not, you kena letak valve. But whatever it is, just make sure that everything is in, there's no condensation happen lah, okay, out of this expander and valve. So kalau you nak condensation, you pastikan you letak dulu heater or heat exchanger. So this one was optimized to heat exchanger. Let's go through one by one. I nak go through one by one dia punya pressure drop, because this is what we do. This is what we do when I mark. Sekarang ni, remember we talk about the sequence kan? So usually we can actually tell what type of fluid package that we use, because bila kita, I think bila kita print workbook, macam mana nak print workbook pun dah tak ingat lah. The one thing I can't remember how to print this workbook. Case. This is no. This is the one that is. No, when we print this, you have to ask that lah. Nanti I tanya that macam mana nak print. I can't remember. Print. Did you see printing?
Dekat file, madam.
Dekat mana? File?
File.
File. Tak ada pun print. Oh, here.
Yeah.
Tengok print. Can we save as this one? I don't know. Okay, I don't know. Nanti you explore lah ya. Okay, now the composition tadi kita dah tukar composition. I memang dah masukkan component master, component mass fraction. How do we do it? Is that you go, katalah you are from the main flow sheet, you go to workbook, and then you go to setup. Dekat sini you add master component fraction untuk komponen that you want to print out. So dia akan keluar dekat sini. This is what I look for. This one I don't want. Component fraction water dengan refrigerant 114. Why I want it? I don't want it. Okay. So these are all the information that I want lah. So whatever that you plug in the values, nanti dia akan keluar 1 star. Jadi bila ada tanda star asterisk, dia ada tanda asterisk, dan I tahu you buat did you plug in the data ataupun dia kira. And then kalau you dekat my stream ni, okay, now I can actually tell what are the information the student put in. Adakah you put in at you set the vapor fraction to be at saturated solution. Then kalau you put it saturated solution, kat sini ada star that I tahu student put it saturated solution, I'll say why you want to do this. So if you set the point ni dekat saturated solution, you have to justify lah. Yeah, because you have to remember when you put it at saturated solution or vapor, kalau tak you put in the value of 1 for dew or 0 for bubble point, means that if any change, a slight change of temperature or pressure, you punya system tu already into phase. Ada vapor dengan liquid which you don't want. Once you ada vapor and liquid tempat blend, you akan susah nak control tau, because the vapor can always change with temperature and pressure. So we want to make sure that your temperature and pressure to be producing one single phase, unless there's a requirement. Do you require it to be at the vapor two phase? Then you have to justify. So you will get the glittering mark lah. That's what I can say. Okay, now okay, let's go to flow sheet. Now I will check pressure drop satu-satu. So the pressure drop in here is 4 bar. That's fine. This is from recycle stream 4 bar, and then we go in here 3.5. So you have set 50 kPa, 0.5 bar the pressure drop. Okay lah. Okay, now this is 3.5, this is 3.15. 3.5 maknanya 35 kPa dekat tube side. Okay, also ni 3.15, and then you increase ke 7.5. So use equipment. So the logical or the sequence of equipment is fine. This one, because I think this is in liquid phase. Okay, so you put in the heater because you want to evaporate everything, because this one the reaction occur in vapor phase. So bila you evaporate everything, okay, into vapor phase, you use your heat exchanger. After that baru you masukkan dekat dalam your compressor. Dalam compressor ni kalau dia ada two phase flow memang dia tak boleh jalan. Dia akan rosakkan compressor you. Dia tidak akan converge pun in high seas. So now the sequence of equipment so far is good. The pressure drop is good. So this one the pressure is 3 bar. Coming out is 2.9. That's fine. Now we have increased the pressure to 7.5 bar because I know this one operates at 7 bar. So that's why kita set lah ni 7.5. Dia ada pressure drop kat sini. Then the outlet is 7 bar. So the operating condition of your reactor is 760 degrees C and 7 bar. So we are good. So the conversion in here is 40%, but I cannot see this. Only you can see this because I tak nak output daripada your high seas. Tapi I think last semester they want it, but I don't know why. In case if you want to open it, I suppose. Okay, now I've been trying. I tried to do the separation of this. So, and I was lucky during this time because I managed to separate everything according to product purity. But the pressure drop I have to use in here is in vacuum. Okay, so the pressure in is 3.5 bar. But then vapor phase is 1. So the tower ni memang kita tak nampak lah, but then you have to extract the information. Dekat mana, what's the pressure like and so on. You must extract the information. Kalau you nak print screen this one pun also no problem. Okay, your reflux ratio also is fine. Kalau your reflux ratio number the 1 times 10 or minus 4, you have to think about it lah. Something is not right. You have to find justification whether it is correct or not. Okay. So that's how I look lah kalau betul ke logik ke tidak kan. So my current value is 5.5, then I'm happy with it, then I'll just proceed. And okay, after that, because this is a separation equipment, so I kena tengok lah composition dekat sini. So dekat composition kat sini, that is 99.5% of my methane, that's fine. And then after that in here, that is composition is 99% of ketene. So that's what we want. That's what my client want. Okay, now this one is acetone. The composition is 100%. It's actually, I set it to be 0.999 because I nak recycle this one. If I were to recycle this, if you want to find the success of how to recycle this, you have to set your temperature and pressure dekat sini sama dengan sini. And close as possible dekat raw material. Okay, which is in here kita guna raw material acetone 1 kan. Okay, now. So when this is over, this is fine. Okay, you cannot let your temperature be like this and pressure be like this because this is supposed to be the product. Okay, so when this is supposed to be the product, your pressure is vacuum, your temperature minus 125. So you have to think, do you want to store your product dekat vacuum and the temperature of minus 125? So you have to make some economical evaluation dekat situ. But I didn't do it when I do this, to be frank. It's just that ni berapa? This one, I want to store this at the pressure 4 bar and the temperature minus 180. So this might not be a wise choice, you see, because the temperature in here is minus 125. This one is minus 180, means that utility, I have to tambah utility kat sini. That is cost. And I have to increase the design of this at pressure 4 bar. But because the choice of pressure and temperature was done this way because I want to keep it in liquid methane. Okay, it's still 99.5%. But to tell you frankly, this might not be the right choice. Okay, because I don't have time to think about it masa I buat benda ni. But you have to use your guts lah. Okay, now in here I increase the pressure because kononnya I don't want to store it in the vacuum, but I don't see why not. You can always store it in vacuum, and then because in here is, oh, I know why. Because this is a vapor phase. I don't want to store my methane in vapor phase, you see. Because at the end of the day, this one vapor phase, of course, because the type of condenser that I use is partial. Maksudnya I punya methane kat sini, I punya ketene kat sini, and then I punya acetone kat sini. So this is the example partial separation of dekat condenser. So I don't want to store my methane in gas because I want to store it in liquid phase. So I try to find information. Actually kalau I nak tukar this one, my saturation temperature berapa. So dekat sini, that's where it comes in. You see, because the pressure drop is 4.5, and I found my saturated temperature kat sini berapa. Saturation temperature maknanya vapor phase fraction kosong kan. Dia ada some value, I think higher than this, lower than this, minus 170 ke macam itu. So I chose minus 180, so that I want to make sure that it's just to be in the safe side, it remains in a liquid form. Okay, but this purely my choice. So if you want to have a proof of what is usually they store liquid methane, what temperature, even better. Maknanya you set the temperature and pressure ni according to literature, the storage of liquid methane. So you have to pop it up. Maknanya dekat dalam you punya report tu you tulis justification, kalau boleh you bold ke gariskan ke apa, justification of choice. Jadi lecturer you nampak, remember I have to read berbelas-belas report. Okay, and it took me about 45 minutes to 1 hour for each report. So if you can help me out to find the information, the keyword from your report, it's much better, so that I can make a quicker decision. What are the marks that I want to give? Usually kalau you senangkan hidup I senangkan hidup you lah, maka tinggi lagi lah. As usual kan. Biasalah macam tu. So kalau dia punya kejap tulisannya dengan cakap putih dia kelang kabut, menangis lah baca. Okay, now, so that's, I can remember now. So I want to store everything methane in liquid phase of 99.5% purity. That's why I choose this. So this one, kalau you tengok, you punya heat flow is 0. Okay, but because I want to maintain the temperature as dekat minus 180, so that's not really matter, just put it there, because it's just that indication that you have to, kalau you biarkan, tak ada coolant yang flow in to maintain the temperature, you know, Malaysian temperature, dia will akan evaporate and meletup ni sebab actually this one dia ada satu line lagi tapi I hide. That is a vapor line. But because I just want to tell you guys that we want everything to be liquid. Okay, the same goes here. I want to, okay, now this is under vacuum. So everything to be in liquid, so I don't want to do it in vacuum, and I increase the pressure to 2 bar lah. Okay, increase the pressure to 2 bar. Now, before the temperature was 125.7, now the temperature is negative 80. So this is okay, I suppose. So because the temperature ni dia lagi rendah lah lagi tinggi daripada this one. Right, the next one. This one, the pressure is 1.8. Now, when you want to recycle, you have to have a purge in here. Even though the flow rate here kosong tau. Nampak tak? Molar flow 0 kg per hour. So even though the flow rate is 0, then we just let it be like that. Whenever it is necessary, then we open this. We close this, we open this. But you just put it to purge. So this is the one. And blah, 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 blah. So we increase. Okay, now I put in the heater dengan pressure dengan pump kat sini because I want to match this one, your raw material ni punya feed. So once this is match 11 ni dengan 19, then baru dia akan recycle. So that's it. I think we have exercised everything dekat dalam dekat dalam the rubrics, the sequence of equipment, why you choose that, the pressure, there's a pressure drop, the separation of product purity separation, the printable, and things like that. I think okay kot. Any question? Ada soalan ke?
Madam, so the condensate from the gas stream, that one,
Yang mana?
the stream 12 13. Oh, that one is condenser lah, the heat exchanger.
Mana this one?
Ah,
Yes, it is a condenser because this one, the vapor phase fraction is 1, and then this one is vapor phase. So dia condensate lah, condenser.
okay, faham.
So it's good for you to masukkan siap-siap you punya heat exchanger rather than pressure dengan you leave it as a cooler dengan heater, because later on when you want to pinch this one is steam kan, this one ada cold, so you ada, this one is this is hot stream, this is hot, this is cold kan, this is cold. So after that, if you want, well, you don't pinch dengan this one lah, you pinch dengan some of the processes yang you nak panaskan, and then you just pinch and masukkan aja dekat dalam ni. Macam this one steam kan? No. Mana? Tak ada semua ni. Okay, one more thing that I would like to mention is why we use vacuum. Sometimes because you want to preserve you punya compound. Okay, sometimes when your pressure is too high in here, your reboiler ni, dekat reboiler ni, the pressure can go up to 100, 200 over temperature. So you have to check you punya, for example, acetone, what is the temperature that it will disintegrate, maksudnya decompose, maksudnya your molecular structure of your acetone tu rosak. Okay, so we don't want that to happen. You want to separate it, but at the end of the day, you rosakkan that compound. So in order for you to, so if the temperature exceed your decomposition temperature, so it is good idea to run this at vacuum, because when you run this at vacuum, what will happen is that your temperature ni dia jadi rendah because your pressure 1.8. So for example yang dekat sini, kalau if you go to 0.5 bar, you can bring the temperature even lower, because we want to avoid your destroy your punya produk ni or any of your compound to be destroyed. So in this case, kalau you nak kata kat sini nampak macam this plant macam tak ada yang kita nak buang, semuanya kita boleh jual. This one is recycle, but inilah condensate ni, nanti daripada sini dia akan jadi waste treatment ni. Refrigerant out ni pun you hantar kot somewhere, I don't know, you have to find out. Tapi macam adalah waste treatment you kat sini lah kot, condensate. Because kalau you ada some compound yang you macam tak nak dan nak buang, macam for example hydrogen ke whatever, you can just send it lah untuk incineration, whatever compound that you want. Any question? Oh, Ted dah ada kat sini. Say hi to Ted, Muhammad Syateh, student kumpulan I. Design project semester ni, semester SEM 8, semester 8.
Hello.
Okay, so kalau tak ada apa-apa, I pass this to Ted. Boleh ke? Ada question tak? Do you have any question?
Madam,
Ya, saya.
Sana kalau steam, recyclekan dia masuk condenser. Lepas tu kita recyclekan steam tu.
I don't think you can recycle the steam, because the thing is that steam ni, bila you katalah this is a condenser kan, this is a condenser, no, this is evaporator. Condenser tak guna steam. Condenser macam ni kita guna refrigerant, because this is hot fluid, you want to reduce it, okay, you want to reduce the temperature to condense it, then you guna refrigerant. Tetapi kalau you notice refrigerant ni, dia punya quality dah bertukar. Quality dia dah jadi the temperature of the quality of the temperature is minus 181.8 compared to this one minus 220. So kalau ada some other heating cooling that you want to do that can actually take up minus 181.8 degrees Celsius, then probably you can do it, but I'm not really sure whether it can be done or not. So you kena cari justification on that. Macam kes yang ni, katalah you want to heat it up, so the quality of the steam also has changed because the temperature in here is 300 degrees C, pressure 3 bar. So bila keluar daripada when you evaporate it, the temperature ni dah berubah jadi temperature dah jadi 132 degrees C. Pressure 2.9. So anytime dia akan condensate. Anytime steam ni akan jadi water bag. So this one kita buang je.
Oh, kalau steam pun banyak sangat, so tak boleh recycle juga Macam kita orang guna condenser nak separate steam dengan komponen tu. So kalau dia banyak sangat steam tu tak payah kena buang jugalah.
I don't get what you mean. You guna steam untuk apa, condensate macam ni?
Dia dekat condenser tu steam tu banyak dekat dalam reaktor, baru keluar dari reaktor. So kita masuk kompresor. Lepas tu terlalu banyak steam dalam tu, kita nak buang, nak separate dengan komponen lain. So pakai condenser kan dia.
Steam, you mean okay now. Your reactor is high temperature, high pressure, betul?
Tak. Pressure dia 1 atm je.
Temperature what?
Temperature reactor tu 550.
550 degrees Celsius. So yang you masuk tu steam ke you masukkan water?
Apa dia punya inlet ke?
Yang jadi steam tu.
Steam.
You memang dah masuk steam? 500 degrees Celsius? 1 atm. Macam ni lah, don't put it in 1 atm. Put it something else. Because kalau you masuk 1 atm, keluar 1 atm, dia tak gerak ke mana pun. Just do some exercise of flip flow lah kat situ. Sebab kalau you masuk satu, keluar satu, memang I tak nampak dan ada problem lah kat flip flow principle tu. So, you are saying that dia still in the steam condition bila keluar daripada reactor tu, but you ada banyak steam tu. The reason you masukkan steam because you nak evaporate your reactor, your component? Bukan condense kan? Or evaporate kan?
Daripada kat mana, dekat condenser tu ke?
Tak, dekat reactor.
Dia dalam jurnal kata lah, dia guna steam sebab dia masukkan air dengan steam sebab reaktor tu endothermic.
Lepas tu?
Dia masukkan reaktor dengan steam. So nanti kan pakai catalyst. Kalau endothermic ada catalyst, nanti catalyst tu ada keki ke apa kan. So dia gunakan combustion dalam reaktor tu untuk naikkan balik temperature. Macam tu lah.
The steam tu dia sebenarnya dia tak campur. It is in the pipeline. I rasa the steam is used to heat up the reactor. Kan? Betul. Yelah, because it is endothermic reaction. So the steam is used to keep the temperature at the temperature that you want. So in that case, your steam tu akan jadi something like dia macam heat exchanger lah, masuk dan keluar. Dia tak campur dengan your mainstream. I nampak tu. Maksudnya dia masukkan air, now it is a fluidized bed ke sebab dia ada catalyst kan? So you masuk yang air tu is the feed and then with whatever reactant that you have, and then dalam tu ada catalyst and then you heat it up. You want to maintain the temperature of the reactor because it is endothermic reaction kan? You guna steam tapi steam tu tak bercampur tau dengan you punya feed tu, tak campur. Sebab kalau campur basah lah you punya catalyst. Sebab dia kata kalau purpose dia hanya untuk keep heat up the temperature, so dia tak bercampur. So you anggap dia macam heat exchanger lain. You anggap dia macam heat exchanger je, macam heat ni. Okay now, so you cannot actually do that dekat high C. So what you need to do is you masukkan heater je, katalah fluidized bed catalyst is something like this. What am I saying? A fluidized bed with catalyst is macam ni lah plug flow ni. So this one temperature dia 750, 144. This one is 760. Ini pun kita masukkan heat. Sama lah macam ni. So this one you tak payah kata steam tu, you don't worry about it. You just letak je heat kat sini. Later masa you design you punya reaction tu, you consider that.
So dalam condenser tu tak payahlah cycle.
Condenser kat mana ni? Ada I tak nampak.
Tak, saya punya tak naik.
Yelah tak, sekarang ni reactor you is not a condenser. Dia maknanya masuk vapor, keluar vapor kan?
Ya, tak bukan condenser dia dalam reactor. Dia lepas keluar daripada reactor tu.
Now your worry just now is to separate the steam. So you don't have to worry because you don't put in steam in here. You just letak Q kat sini. So you letak the temperature process temperature you kat sini. So you do not have steam kat sini. Because in the actual principle, steam tu you tak boleh masuk, kutip nanti betul lah caking. Because steam tu is water. And the end of the day, dia akan absorb. Dia akan hydrate the catalyst you, akan menyebabkan caking. So there's no way that your steam is dicampurkan dengan catalyst you. So this is exactly like what you have to do.
Okay, faham madam.
Alright, that's great.
Thank you madam.
Sama. Okay, probably we need to ask Ted. Are you here, Ted?
Yeah, I'm here.
Thank you. You are here. You save my day. So I can start presentation. Okay, everybody. Ted is my design project student. Already in semester 2. You design apa, Ted, semester ni? Tak ingat. Absorber tak. You are designing storage tank. But I don't think that's an easy job. That's because you have to include the heating element kan, benda-benda gitu. You still have to calculate the heat transfer. So you will exercise it. So the thing is that dengan Ted punya equipment is that dia quite simple kan, Ted kan? So this semester ada someone actually designing nitric acid kan, Max tadi, Maxwell? Nitric acid kot. So ours is hydrochloric acid. So Ted, I need your help to show what you have done semester lepas, and also I think some of them need to see how you do the simulation for absorber sebab I tak actually cover that, and probably you can share some experience lah how to do it, and the cutter, and you guna different flip package for different stream and things like that. Okay. Okay, nak minta you present lah. Kalau you boleh present, ada kan output you?
Ada.
Thank you.
So this is hydrochloric acid simulation. So dekat sini kita pergi dekat properties dulu lah. Dekat properties macam biasa, kita pilih kita punya komponen. So ni saya punya komponen. Dengar tak? Doktor dengar tak?
Dengar loud and clear. Thank you.
So bila kita dah pilih semua komponen, and then kita pergi ke fluid package. So fluid package dekat sini saya guna 2 fluid package. Untuk kita pilih fluid package kita tu, kita kena study lah kita punya chemical reaction. So apa yang perlu guna untuk kita ambil sebagai flow package kita. So untuk macam overall macam 90% saya punya simulation kita orang guna Plank Robinson untuk basis 2. Basis 1 ni extended NRTL SRK ni kita orang guna untuk stimulate absorber saja. So nanti kita orang akan guna kata tu untuk nanti saya tunjuk. So kena set reaction. Set reaction ni kita ambil conversion semua. Then simulation. So this is our absorber. If you can see, this is a cutter.
Apa function kata tu?
Max kena cakap kuat sikit, tak ada apa dengar tadi.
Oh, my mic was on kah just now? Okay. Oh, sorry.
Function kata ni adalah untuk kita tukar basis. So maksudnya kalau kita tengok dari sini, ini yang masuk ialah stream 9, yang keluar stream 10. And then kita tengok dia punya worksheet. Make sure dekat kata ni temperature akan sama, masuk dengan keluar. Kat sini untuk penggunaan kata maksudnya dekat stream 9 dengan stream 10 ni adalah penggunaan basis yang berbeza untuk kita stimulate absorber ni. Macam stream 9 ni kalau kita tengok dia pakai basis tu. So dekat sini kita boleh tukar. Tapi saya pakai basis tu sebab tadi macam saya cakap saya guna flip package Plank Robinson kan. So kalau untuk saya punya stimulation ni nak stimulate absorber, saya tak boleh pakai Plank Robinson, saya kena pakai extended NRTL tu. So dekat sini kita akan tukar pada basis 1 which is extended NRTL tu. So fungsi kata ni adalah untuk kita tukar flip package. Tapi kena make sure temperature in dengan out untuk kata ni sama. Dia punya operating temperature.
Ted, sorry, tolong tunjuk sikit kata tu, is it kata tu you bawa ke situ ke macam recycle tu ke, ataupun bila kita set dekat T100 tu bila kita set kepada basis yang lain dia terus keluar kata?
Okey, kejap
Oh, it's there.
Ya.
So you just masuk je lah, macam recycle lah tak function dia?
Ya.
I see.
Nanti ambil je mana-mana stream masuk dengan keluar.
So after you punya stream 10 tu dia terus dah guna NRTL dengan ni SRK?
Ya.
I see. Sebab dah tak work why you decide that? I can't remember lah, that's what you buat sendiri ke?
Sebab satu kita tak dapat absorber tu dia punya proses dia tu macam tak logik. Maksudnya dia tak dapat kita punya produk kita dapat sikit, dia punya mass fraction kita dapat sikit, and then yang keluar untuk atas ni banyak.
I see. So that's the reason you change the punya flip package lah kan?
Yes.
Yeah, you are allowed to do that lah, not an issue here. Tapi itulah kalau boleh justify lah, masukkan dekat dalam ni.
Yeah.
How long does it take for you to do this? All in all.
All the time dia.
All the
4 bulan lah, 4 bulan.
You start minggu ke berapa Ted masa you buat?
Saya tak ingat lah tu.
Rasa quite early juga kan? Macam minggu ke-6 kan?
Tentu saya buat seorang je dulu. Saya tak minta tolong sangat mic.
Yelah. Sebab dia buat energy balance kan? Okay. Boleh. Lagi soalan ni you all. Okay, mungkin hari tu, there's a problem. Hari tu how do you find that benda ni kena operate high pressure? Ingat tak yang dekat absorber kan it has to be high pressure so that you can do the separation. Berapa pressure dia? Cuba dah buka sikit tak you punya tower tu, tengok macam mana nak buat. I pun tak nak buat dekat design. This is what it looks like. 28 bar
Ya.
Nak tengok efficiency boleh tak?
efficiency.
Dekat.
Efficiency maknanya dia punya yang keluar dekat 11 dengan 12.
Tak, dia punya tray efficiency.
Dekat kalau kat high seas it is theoretical max.
Oh.
Macam distillation column lah, everything is theoretical. So later on bila you kena design absorber ni I think kena bahagi kot. I don't know, I think siapa yang buat absorber ni dia tak guna tray, dia guna pack. Kan Ted kan? Siapa yang buat dia? Amalia?
Guna plate.
Amal kat sini Amal. Tapi kat sini dah kata pack, tapi dekat design tu kenapa ada plate juga Ted eh?
Dekat mana design?
Tu ada number of stages tu. Memang ada
Memang ada. Dia require benda tu.
Amal, tapi kalau you design absorption tower memang tak ada stage kan?
Tak ada. Okay, tak ada lah.
Dia memang macam ni kot. I don't know.
Design selalu dia akan ada number of plate. Itu je, number of stage. Tak pernah jumpa pula saya.
Okay. What happen kalau dekat P1 dengan PN tu you ada some pressure change? Bila sekarang tak ada pressure change pun okay
Make sure pressure P1 dengan PN ni pressure lagi besar daripada pressure inlet. Water inlet 1 dengan maksudnya top stage inlet dengan bottom stage inlet.
Sebab benda ni dia tak ada yes. Sebab this one is not distillation column kan?
Ya.
So yang atas water inlet tu dia akan flow through gravitational flow, tapi still dia akan ada pump because 2.8 bar tu is the one yang dekat bawah S12 tu kan?
Ya.
So bottom stage inlet tu dia vapor, so dia akan kena lagi tinggi lah daripada P1 tu. Berapa pressure 10 tu? Worksheet ni tengok worksheet. Worksheet tu tengok. Water in pressure 30 bar. Stream 9 tu masuk 50 bar. Tinggi ni pressure Ted. Memang macam tu pressure change tu memang tinggi gitu
Ini yang masuk.
Boleh optimize lagi kot. I don't know. Amal, you optimize lah benda tu. Tinggi sangat pressure change tu kot.
Ni yang kita nak tengok. Ni.
Yelah, pressure change tu tinggi sebab inlet dia mana? Pressure, inlet mana? Tak nampak pula. Inlet gas tu dia tengok 50 bar kan? S10 tu. Is it true?
Ya, 50 bar.
Itulah. You bayangkan 50 bar nak turun kepada berapa? 28 bar kan?
Ya.
Tinggi tu. Amal, cuba you jangan tengok sangatlah ada pressure ni. Kalau boleh you tolong optimize sikit benda ni. Boleh Amal? Nanti kesian orang buat pinch.
Boleh.
Mic pening nanti. Cuba tengok sikit lah. Tengok 10 kali tengok pun jumpa lagi. So jumpa lagi here and there ada isu. So macam tu lah you all. Jangan lagi 2 minggu nak hantar baru start high seas. It's not going to work. Nangis you. Ingat kosong nampak. So your PFD will be depending on your high seas. So maksudnya you don't present PFD lain, your high seas lain. So nanti you ada industry panel. So the feasibility of your plan tu is depending on you punya PFD you lah, which is depending on high seas. You ada banyak tak kena tanya Ted masa you punya presentation dengan
Tak, saya kena tanya dia punya absorber je.
Pressure tinggi kan?
Tak, dia tak sentuh langsung pasal pressure ni, dia tanya pasal kita punya produk, kita punya purity tu je.
Check sikit ni tadi Maxwell dia nak tengok product purity. So yang itu what happened dia punya tu 61 because you want to sell 38% water, 38% HCl kan?
Yeah.
Because that's what the customer wants, because yes. So capailah 38%. It's an aqueous kan?
Reference lah.
Macam ni you set aqueous tu? Ingat tak? Nitric acid pun should be aqueous rasanya.
Sini ni kita akan guna cooler.
Tak, maksud I aqueous, benda tu jadi aqueous phase tu. Macam mana? Tak faham.
Hari tu lepas tukar basis tu terus dapat aqueous tu lah.
Oh, maksudnya bila Peng Robinson dia tidak
boleh
support aqueous kan? Memula yang basis sebelum tu apa, Peng Robinson kan?
Peng lepas tu kita pakai NRTL, SRK, NRTL.
Yep. So what I'm trying to say is that dekat S12 tu kalau you buka, cuba klik kat situ. Okay, bila you klik dekat situ, dia ada keluar aqueous phase. Bila you guna Peng Robinson, dia tak keluar aqueous phase kan? Hari tu kan dia macam liquid dia determine.
Ya, dia keluar liquid phase.
So, one thing that you want to know, bila dia tukar dia jadi liquid phase, maknanya dia separate kan water dengan HCl tu is two different component. It's not aqueous. So that is not right. Okay, so those yang produce acid ni, yang ada aqueous ni, so you have to find fluid package yang support macam NRTL tu, because it's a liquid phase kan. So that's why dia keluar aqueous phase. So benda macam ni yang I akan tengok bila kita mark your design project. Kalau dia keluar vapor liquid memang dia separate salah lah benda tu.
Dia separate, dia tak absorb. Antara
dia
dengan liquid phase tu dia tak absorb. So kita tak dapat produk in aqueous lah.
The property tu salah lah sebenarnya, dia tak properly predict lah maksudnya.
If kalau nak pakai NRTI tu boleh, tapi macam doktor cakap sebelum ni, make sure dia punya principle fluid flow tu pressure tak tinggi lah, tapi sebab kita punya fluid flow punya pressure tinggi.
Okay. So you guna NRT SRK lah kan, bukannya ideal. So tukar kat situ kan.
Ya.
So to flare tu, cuba tengok sikit to flare tu. So this one that you separatekan kan waste stream tu, that is a waste treatment. To flare yang dekat composition, tengok composition dia tak apa. So it contain HCl. Aduh dia tak banyak ni sebab 5 kg per hour, sikit sangat tu. That is small amount, 5 kg. Tapi still we have all the gases tu, kita buang lah kot. Waste stream tengok. Composition. So 96% of water. So good enough. Ada sedikit HCl dalam tu, so okay lah. Tu boleh buat waste treatment. So yang bawah tu tak dekat keluar V100. Composition. So you have 37%. Okay, sebab dia campur kan, dia output atas. Bawah tu
dengan second absorber.
So dia jadi 37. So tutup ni so okay lah kan, we are selling it at 30 berapa, 37
Ya.
So we use the second absorber because the first absorber tu dia tak boleh nak buat all the job kan.
Ya betul.
So you need second absorbers.
Betul. Kat sini lah banyak lagi kita punya produk yang keluar sini.
Ada 64% HCl lagi. We cannot throw that away. So that's why we put it separated in the second absorber. So if you need second absorber, you kena justify. Kalau tidak, kita akan kata kenapa tak boleh separate everything on the first absorber. Or probably if you don't want it to be in series, you can do it in parallel. Jadi we can see, oh, because it's too the feed is large, so menyebabkan you need to in parallel, two absorber in parallel. So mungkin that is a safer bet kot that rather than buat dalam bentuk series macam ini. Yelah, bila buat dalam series saja kan, orang yang mak tu kata, oh ni efficiency tak optimise ni. Efficiency of the first separator, but it could be because it's too large. So if you separate it into two parallel, nampak macam oh okay, dia tak cukup.
Ya. Sebab kalau based on kita orang punya reference pun, after keluar absorber ni akan masuk like scrubber. Untuk macam kita guna balik lah hydrochloric acid ni, yang hydrochloride gas untuk jadikan hydrochloric acid ni aqueous. So sama lah fungsi dia.
So that is a scrubber? Okay.
Sama kalau kita macam saya tengok, saya study sebelum ni, kalau untuk dia orang design scrubber, dia orang akan guna equipment absorber ni jugalah.
Okay. Oh, okay. Patutnya I suruh someone design scrubber kat situ, bagus juga. Tapi I don't think make much difference, sama je scrubber dengan absorber kan.
Sama.
Sama doktor, scrubber sebab sama je.
Apalah, biarlah tak pergi design the storage tank tu. Okay. You jangan merendah-rendahkan diri you. It's not as easy as you think. Someone is designing storage tank dekat consultation firm, so you can do the same thing. Does not really matter. Okay, I think ada sesiapa nak tanya soalan tak? You only diam aje.
Doktor.
Ya, Afiq.
Yang hydrochloric acid ni kan, production capacity dia berapa?
Production capacity?
Amount yang produce. Berapa banyak per year?
Oh, kalau macam kita orang buat, berapa Amal?
Apa? Kami tak dengar.
80,000. 80,000.
Betul 80.
Di mana lupa pula.
80,000 kilogram ke 80,000 ton?
80,000 metric ton. 80,000 MT. Per annum. Lepas tu you macam ni you adjust production of HCl ni dapat 80,000 This one per hour kan? You ada buat adjust button ke dengan yang depan ni? Tak ada
Tak ada. Yang tu kira tangan.
Guna tangan.
Kira manual.
Okay.
Sebab ada ratio jumpa tu.
Okay, now I nak beritahu dengan you sebenarnya ada trick dia. So katalah you dah buat macam ni. Okay, tolong tutup tak? Nak show. Trick dia, you does not really matter. You know already the ratio chlorine dengan hydrogen tu. I think this is equimolar kan, tak kan? 1:1.
Ya. Betul.
Okay, katalah you masukkan 100 kg per mole per hour of chlorine, 100 kg per hour of hydrogen. Lepas tu you letak apa nama? Bukan set.
Adjust function madam. Betul.
Bukan adjust. Dia ada set, ada adjust. Dia antara klorin dengan hidrogen ni you boleh tak? Maknanya kalau I ubah hidrogen ni kepada
betul lah.
Apa nama? Cuba tengok balik yang bawah tu.
Ni set ni.
Itu set tak? Lagi bawah dia. Atas. Oh, tu set dekat situ.
Ni set.
Okay, now sekejap. Set tu sebenarnya you boleh tiekan antara hidrogen dengan HCl ni. So maksudnya nanti katalah hidrogen ni 100 metric ton, hidrogen ni you produce, you masukkan 100 kg mole per hour, you dapatkan HCl ni, tapi you kata you nak HCl ni 80,000 metric ton per annum. Maknanya kira lah tukar kepada hour, you guna set button tu, you tie kan, you ikat dengan HCl production yang keluar dekat storage tu dengan yang hydrogen masuk tu. So dia akan adjust back, tetapi satu isu dengan TAD, you punya ni TAD,
Ya.
dia samalah. Dia sama juga macam yang you guna adjust tu. Satu isunya, boleh tak tolong tutup balik tak nak tunjuk? Sekejap. Ada satu lagi command yang boleh ikat antara klorin dengan hidrogen. Maksudnya bila kita tukar, dia set ratio tau. Ya Allah, tak ingatlah nama benda lah tu. Ratio. Itu tak ratio, bukan set. Ada tak? Ratio controller. I don't know. That one is dynamic tu, blank column. Recycle. Yang bawah sekali apa? Yang ada nak panah tu. Equilibrium. Ya, tak ingat lah. So, apa yang you buat adalah you boleh tiekan antara dua tu, maknanya kita set dia equimolar. Maknanya banyak tu hidrogen, banyak tu klorin. Jadi, bila HCl you ni kata you nak 80,000 metric ton per annum, dia akan tukar dekat hidrogen, at the same time hidrogen tu akan tukar juga klorin tu punya feed. Jadi dapatlah semua.
Faham.
Kan? Tapi itulah, you punya ni complicated, tapi bila you kira tangan, okey lah. Tak senang kira tangan lah. Maksudnya bila you all dah habis, semua dah dapat, baru tukar kat depan kan, kan? Kat raw material.
Ya, tukar kat depan.
Maknanya bila dah converge baru you buat you buat
Ya.
betul. Tapi ada risiko sebab kalau katalah dia besar, dia tool huge, so one of your equipment ni could be tak boleh nak support. So sepatutnya you ada two in parallel, tapi sebab dia too huge, dia tak boleh nak support. You faham tak soalan? So you ada risk lah untuk dia tak converge.
Faham?
Okay, lagi soalan?
Untuk workbook punya
Ada tunjuk kat dia orang tadi, nak print tu macam mana? Macam ni kalau kita guna dekat TeamViewer, macam mana nak import untuk print ke kita? Untuk masuk dekat
TeamViewer tu
sekarang ni katalah I guna TeamViewer, lepas tu kita nak print kan, dia punya output tu, workbook punya print tu, macam mana nak savekan benda tu jadi save as jadi PDF ke? Boleh lah, printer dekat ni macam tak boleh buat.
Ya ke? Saya right click macam ni je print data sheet.
Lepas tu, tekan. Tapi ni you punya kat rumah kan?
Ni dalam PC saya lah. So kita preview dulu.
Tadi dekat printer kalau this is what it looks like. Ada nampak kan tak kan kita punya flip package? Nampak tak? Ada tak anywhere?
Flip package tak ada sebenarnya. Sebab kalau ikutkan dekat sini dia ada unit out, energy stream, composition, so kita boleh pilih lah. Selalunya akan print semualah.
Kat mana tu kan tadi?
Ni preview ni.
Tak ada right.
Saya right click dekat workbook punya ni, saya letak kat sini, saya right click je.
Print data sheet.
Print data sheet.
Cuba tengok print setup. Boleh tak buat save as?
Sekejap. Kalau tekan print, bila print nanti dia terus save.
Oh ya ke?
Kita boleh letak ni ke PDF.
Save as PDF kan? Tu print to PDF tu. Okay. So kalau print PDF dan you boleh save, lepas tu you import masuk dalam you punya apa tu, Google Doc lah kot. Google Doc pula. Apa benda tu? You punya Google Google Drive you. Save lah. Lepas tu you boleh masukkan together with your printable output untuk dengan projek you. So any other question?
Doktor dah tunjuk ke yang tukar mass fraction tu?
Dah tunjuk dah. Dah pandai dah dia orang. Don't annoy us. Ada cakap dah, I will get annoyed kalau nak nampak more fraction. Any other tips that? Bersabar
Kena buat banyak kali lah.
Dia bersabar.
Buat kalau dah dapat, save dulu. Save as lah, banyak tekan save as. So dia akan save another file lah.
Banyak version.
Banyak. Saya rasa saya punya dekat 50 file kot untuk IC untuk ni saja.
50?
Ah,
Dapat pula supervisor duk suruh tukar je. Dapat supervisor tak ada komplain apa-apa, okey lah. Supervisor suruh tukar ni lagi lah banyak kali kena buat. 4 months agak-agak. Tapi the one yang you hantar masa final project, final yang dengan report tu pun not so good kan?
ya.
So it
Kita
affect.
keluar dari Absorbtion ni terus dapat produk. Tak ada atas ni. Yang stream 11 ni terus ke flare. So macam
Yelah, ada memang ada isu masa tu.
ah,
So the thing is that markah untuk report diberi on the first part tu, masa yang you hantar the first part yang kepada examiner. So because we are konon-kononnya the content expert lah, yelah we have to mark the content. So markah kat situ memang tak boleh ubah lah, but then after that you have to present you punya kerja ni in front of panels, again the lecturers and the industry panel. So you are expected to correct it lah. Tapi I rasa those yang buat design project kebanyakannya yang I jadi judge dekat panel yang dekat dalam bilik tu, dia orang tak betul kan pun. So bila tak betul kena sekali lagi lah. Dah lah kat report banyak merah sana sini, kata tu salah ni salah. Tak betul kan kan? Yelah, because the pressure. Berapa lama? Dalam seminggu je tak antara dia bagi feedback dengan present dengan industri. Seminggu kan? So macam tak sempat kan, nak betulkan kan?
Kita orang esok nak present pun malah tu meeting lagi kan.
Tapi you sempat kan betulkan kan?
Tak sempat.
You pun tak sempat present sebelum hantar ke design ke panel tu?
Tak
Sempat lah.
Sempat lah tak? The one ni
tak sempat.
cantik ni ke?
Tak
Kan?
sempat.
Because I was harassing you day and night to do this. Okay. So ada apa-apa soalan ke ni? Belum dapat 7 ni. Ya Allah, senyap je. Lepas ni kita tak ada tunjuk ni dah, buatlah sendiri.
Tengok YouTube je. Kita orang dulu part 5, part 6.
Part 7 ni diorang ni?
Tak, saya dulu belajar YouTube je.
You jangan banding. Diorang ni I manja, I dah bergeria ni.
Apa?
Orang kena appreciate lah doktor nak jaga orang. Kita orang dulu masuk kelas, asal hijau jalan.
Betul. Sakit.
Rubbish in, rubbish out. Itu I punya motto. Rubbish, warna hijau, warna biru tak semestinya, converse tak semestinya betul. You can put in, rubbish out lah.
Betul.
Okay. Okay, kotak dia orang ni senyap je, segan je you all kan. Afiq.
Yang macam saya punya natural acid kan. Ada that one equipment tu, macam condenser. But then condenser tu dia convert nitrogen dioxide into nitric acid. So yang tu boleh ke untuk like macam implement yang dalam, kita kena guna satu implement, let's say macam double faham tak?
Afiq, sebenarnya I tak berapa dengar soalan you. Seriously, I tahu you buat nitric acid, lepas tu dengan condenser, lepas tu
ada that one equipment, ada satu equipment right after ammonia converter. Okay, ada satu condenser. But then condenser tu macam ada reaction takes place juga dekat situ. So boleh ke kita guna?
So maksudnya instead of condenser, it is actually a reactor lah. Kalau reaction takes place.
No, dia macam
Yelah, maknanya
ya kot.
kan, sebab because
Yelah,
dekat heat exchanger, you tak boleh dekat heat exchanger, boleh ke you letak reaction kat situ? Kalau boleh attach, attach lah.
Yang saya confuse tu dengan PFP dia tu sebab dia state kat situ condenser tu macam dia somehow convert O2 into nitric acid before they proceed to absorber untuk further purifykan nitric acid tu.
Okay, kalau I jadi you in the safe side, I guna conversion reactor.
Okay.
Maksudnya kalau dia condense masuk vapor keluar liquid lah.
Betul.
Maksudnya you ada Q kan? Q taken up heat kat situ. So you condensekan everything in the reactor. Lagi senang, rather than you, memanglah dia sebut condenser tapi sebenarnya you have to you kena fikir evaluate balik. Sebab kalau you letak dalam heat exchanger, because at the end of the day macam tag ni pun tak ubah ni tag kepada heat exchanger. So kalau you ubah this one kepada heat exchanger at the end of the day, nanti reaction tu susah nak identify, nak masuk feed tu sebab heat exchanger feed dia satu je. One in one out.
So
I mean dekat tube side lah, dekat shell side tu is a you punya refrigerant kan. So instead of cracking your head dekat condenser which you think is energy balancing equipment, you masuk je dalam conversion reactor. Senang gitu.
So kita boleh improvise lah kan?
Later kalau you dah ada kinetic data, you boleh lah improvise. Kalau tidak, tak adalah kita nak garang sangat kerja you suruh buat kinetic ni.
Saya tengok reference pun macam like mass balance dia pun konsep dia pun macam memang dia guna konsep condenser macam two inlet stream, two outlet stream.
Maknanya dia yalah
Konsep
kalau sekarang ya I faham. Tapi kalau you look back, cuba you tengok dekat tag ni produk ni dekat C ni kan. Dekat conversion reactor ni sebenarnya dia ada two inlet. Sebenarnya yang heat dia masuk dalam tu in real life dia guna refrigerant atau steam. So dia adalah outlet dia. Tapi in this case dia tak nak complicate things. So dia assume je yang itu is heat added without complicating the simulation that benda ni sebenarnya heat exchanger. So whatever heating element yang ada dekat equipment, kalau you tengok dekat semua ni, this is not electrical except for pump, compressors tu is guna fuel. Okay. Tapi kalau macam untuk conversion reactor ni, actually dia ada heat in, heat out. So bila kita nak supply heat kepada the reactor, it goes into the heat exchanger punya principle. So untuk converge-kan you punya simulation for part 7 ni, it's adequate kalau letak any reaction letak dalam reactor. So but you have to understand, sekarang ni macam case Nur Adah tanya tadi, steam masuk dalam fluidized bed kan. So we don't include steam, tapi steam tu sebenarnya heating element je. So might as well you just guna conversion reactor. You heat it up. Berapalah temperature nak ikut suka you.
But kan madam, I also do the nitric acid. So yang actually the condenser tu, kalau ikut the one yang I read from lah, dia cakap the nitrous gas dia akan masuk the condenser, lepas tu dia partially condense, and then like some of the condensate dia akan jadi acid, and then the gas will be further condense lagi lah.
Tak apa, betul je, boleh je. Maksudnya boleh tak, sebab sekarang ni there's a reaction occur kan? Ke hanya condensation ni, dia tak ada reaction?
That's I'm not sure. So they say in the one that I read from the journals that I read, dia cakap condense.
NO3.
Dia cakap condense.
Sekejap. Nitrous acid is what? HNO3.
HNO3, yes.
So dia tak ada reaction, dia terus jadi acid dengan gas kan? Betul?
Dia ada acid flow, dia ada gas flow.
Itu tak apa benda you guna?
Tak, saya tak tahu.
Flash drum.
Oh.
Maknanya whatever you want to condense, you condense dekat dalam flash drum. Lepas tu you boleh separate gas dengan liquid. So dia tak ada reaction lah kat situ kan?
Betul.
Kan Aman?
Betul.
State agree.
Yalah.
Dia akan tolak gas tu keluar ke atas.
Sebab dia nak condense untuk jadikan acid je.
So actually flash drum je lah.
Tapi dia bukan aqueous you all. Maknanya acid tu 100% lah HNO3 tu.
Yang tu saya tak go further lagi sebab
Maybe at
ada
first
dia punya
kot.
mass balance dia.
You all kena tengok balik dekat reaction yang belakang-belakang ke apa. So memang actually it's a good idea you terus buat guna HISIS rather than you guesswork benda-benda gini.
Oh
Terus.
ya. Yeah.
Kau tidak tak nampak kan tak kan dulu ni tak nampak kan tak kan?
Saya terus buat guna IC terus.
Terus. Jadi you nampak the pressure dia, you guna pressure temperature berapa, dia punya phase tu berapa, you nak tukar,
Yang flow rate dia tu just letak basis apa-apa dulu.
Letak je.
Letak dulu. Lepas tu nanti dah kira baru tukar balik.
Oh, okay. Thank you.
Faham. Good. Lagi? So far nitric acid je tanya ni, orang lain tak ada tanya. Banyak projek you all kan kali ni kan?
Nitric acid pun dah pening tu.
Betul.
Nitric acid you akan pening sama macam
hydrochloric ni ke?
Memang pening. I pun pening itu masa dia mula cakap. Tak ada decision column, itu absorption.
Oh, tak ada DC juga ke?
Tak ada, senyap sama macam you all ni.
Tak ada sebab
Absorber.
ada certain yang pakai DC tapi tak tahu lah, tak faham sangat konsep dia tu kenapa pakai DC.
Okay, aku syukur lah tak ada DC. DC lagi complicated tu.
Ya tu. Syukur.
I rasa DC macam okay je. Tapi I cuba 3 kali dapat jawapan lain. Mula converse tu, tu tak converse. Pening. Tapi jangan put off lah sebab benda tu memang kena perlukan kesabaran. So I suppose macam case you juga Ted kan? Dekat stream 9 ni dia memang pure HCl kan?
Hydrochloride gas.
Yelah HCl pro. Lepas tu and then after that baru you tambah water untuk jadikan aqueous kan dekat absorber.
Untuk absorb untuk jadikan aqueous.
Sama lah prinsipal I rasa. So you all daripada masuk dalam flash drum, so dia akan ada liquid, ada gas. So mungkin yang liquid tu you tambah water macam case ni untuk absorb jadi aqueous. I don't know. Ikutlah proses macam mana. Sebab you memanglah dekat dalam sistem tu dia tulis distillation column tapi you can always change it. You kena try banyak kali. So jangan lama sangat duk fikir pasal PFD because you are not supposed to follow the pattern 100% or else you akan di-charge sebagai plagiat. So it is only a guideline. So bila you dah ada guideline, then HISIS will tell you the feasibility of the process whether bila you guna temperature pressure equipment tu logik ke tidak, boleh jalan ke tidak. So jangan worry sangat. As long as dapat you got direction right, jalan je lah. Gunalah.
Jangan ikut sangat reference tu.
Boleh lah reference campur-campur lain-lain kat mana. What Ted's trying to say is that jangan ikut, you don't restrict yourself to one reference yang kat pattern tu kan Ted kan? That's what you mean right?
Betul.
Nanti you pening sebab dia memang kat pattern dia tak disclose all. Tak begitu semua. Okay, lagi soalan?
Saya nak tanya.
Ya, Anis.
So kalau macam untuk progress sekarang ni dia start HISIS dulu lah. Dia macam work backward lah from HISIS then material balance and energy. Macam tu ke?
Yes, correct. Sebab kalau sebab dulu-dulu masa you buat your mini plant, mini design project, you tak belajar HISIS lagi. So that's why you are forced to do the balance and method energy balance guna tangan. So I'm sure you have a lot of calculation to do. So sekarang ni you dah pandai HISIS. So you buat guna HISIS dulu, lepas tu nanti you will try to prove it back. I don't know, Ted, share experience sikit. You energy balance kan dengan Mike?
Saya mass balance.
Oh, you buat mass balance? Siapa buat energy balance dengan Mike?
Dia dengan Mike. Dia.
Oh, Jiha. Okay. Ya. So, macam tu kan, Ted, you buat backward calculation kan? Maknanya you follow HISIS baru buat your mass kan? So far okay kan you punya masa lecturer yang mark you punya material balance itu dia kata okay kan, dia tak adalah kata benda tu salah kan?
Tak ada. Waktu present pun okay je.
Okay. Maknanya you kena buat HISIS dulu baru you boleh buat yang lain-lain. kalau you buat mass balance guna tangan, energy balance, lepas tu you nak paksa HISIS ni ikut you punya result energy balance, memang tak dapat. Not going to happen. Sebab remember this one ada fluid package kan. So you tukar-tukar fluid package. Fluid package tu actually dia predict the property which you are not able to calculate it guna tangan pun.
Kalau korang dah buat macam rasa benda tu betul tapi still tak dapat result yang okey, try main fluid package lah, sebab fluid package tu penting tu.
Okay, lagi? Ada 10 minit lagi ni sebelum habis kelas. 8 minit. Any question? Ya dah, semua happy, semangat nak buat HISIS dah.
Doktor.
Ya saya, Atira.
Saya ada soalan. Semalam kita orang macam dah buat, saya pun buat nitric acid juga. Kita orang macam PFD dah kira settle. Cumanya dia punya main equipment untuk design nanti jadi SBC punya concern sebab kita orang macam tak cukup equipment untuk setiap seorang. Kan tadi yang Syati ni cakap dia lepas absorption tower first tu dia terus produce kan, tak ada absorption tower yang tak ada yang second tu. Macam ni, macam awal-awal kita still macam tak cukup equipment. Kita boleh proceed ke? Macam yang Syati buat tu dia ada satu je absorption tower. Lepas tu faham tak maksud saya? Macam mana nak proceed? Macam
Atira, I faham maksud you. Ini adalah concern group kami juga masa mula-mula. Masa mula dia produce, saya kata ini dia equipment, nak design apa ni kan. So that was my concern as well. Tapi after dia optimize the condition, masa mula tu hanya ada T100. Tapi bila kita tengok something is not right there, purity tak capai and so on. So that's why kita ada 2 tower ni. Tetapi even though ada 2 tower, only one person aja pun, I assign seorang aja pun yang design satu tower. Because I tak nak student I design 2 identical tower. Why? Because masuk ni water, T100 ni masuk water, T101 pun design water. So kalau you don't worry about it because macam Ted, dia terpaksa design tank. V100 kan Ted kan?
Betul.
Dia stress, dia kata kat I macam mamain je Ted. Tapi sebenarnya it's not. The challenge is there because you have to keep it the temperature constant. Yeah, you ada nozzle vapor out, benda tu ada. So kalau kita tengok daripada sini, the thing that you can design, mungkin a reactor is a must. Jangan sampai tak ada sesiapa pun design reactor. So dalam kumpulan I, ketua design reactor kan? Nazira ketua, dia design reactor. And then Amal design tower. T100 ke T101 Amal?
Saya buat T100.
Kenapa I suruh pilih T100
Tak, saya pilih sebab dia dua-dua tu benda yang sama.
Oh you yang pilih. Okay, tak apalah. So I pilih Amal dia pilih sendiri, kata you nak absorber. Kemudian siapa? Alia heat exchanger kan?
Alia heat exchanger.
Siapa
Mic cooling tower.
Mic apa? Cooling tower?
Mic cooling tower.
Cooling tower kat mana
E100. Dia before absorption column tu.
Before.
Dia macam heat exchanger tu.
E101 tu kan? E101. So that
yes.
Ni.
Yeah. So that is cooling tower kan?
Ya.
So ada someone is designing cooling tower. Alia designing Aida bukan?
Aida separator.
Aida separator yang itu. Alia kan seorang lagi?
Alia heat exchanger.
Heat exchanger yang mana?
Yang tu tak tahu lagi sebab dia pun tak ambil lagi.
I kata okay now Atira, macam kes ni dia kena design 2 heat exchanger. Ada 2 orang kena design heat exchanger, seorang Mike which is a cooling tower, another one Alia, I suruh dia buat pinch dulu. So selalunya the best way to do it is that to instead of heat exchanger macam Ted buat ni, dia kena tukar kepada instead of heater and cooler ni dia kena tukar kepada heat exchanger. Jadi I suruh Alia buat pinch dulu. Okay, dia kena pinchkan dulu, lepas tu dia kena design heat exchanger yang telah dipinchkan. So all in all semua dah ada lah. Ada yang flash drum, absorption tower, reactor, cooling tower. So selalunya heat exchanger ni boleh 2 orang lah. So satu yang heating up, satu cooling down lah macam tu. Tapi sebab satu heat exchanger, satu lagi cooling tower is two major things lah. And then sebab tak ada benda nak design, I takkan nak bagi compressor kan. So I bagilah dekat tank tu yang paling simple sekali, yang dikatakan sebagai simple tu. I just want to see is that simple or not. So don't worry about it, you just proceed aja.
Okay. Sebab saya punya SV ingat heat exchanger tu tak payah design.
Siapa SVU?
Maiden Sharina.
Kena
Sebab
design.
dia bio, so dia macam tak tahu sangat.
Tak adalah, dia dah lupa tu. Dia baru balik daripada PhD dah 4 tahun dah duduk fikir pasal benda lain, tiba kena fikir design project, dia pun dah lupa. So heat exchanger can design. Don't go and design compressors. Compressor tak perlu kot. Pumps, you don't have to do it. Well, somebody designing it, kalau tidak macam ni nak ada pump dengan compressor kan? Somebody design it if you want it. I punya student I yang first design project I pernah bagi compressor. Tapi kesian lah dia. Tapi amazing apa yang dia buat. One lah dia dapat. Tapi dia pernah design compressor, so it's going well. Tapi cuma I tak rasa lah compressor is any equipment to be designed. Itu more on mechanical punya kerja lah. Untuk chemical tu tak banyak kat situ. Tapi it has lots of combustion. Siapa yang dapat kena design compressor menangis lah. Heat exchanger kan, sampai 2 bagi.
Okay. Thank you.
Yeah. Lagi?
Okay, madam, last question.
Yes, next.
Okay, so like nitric acid, right? The raw materials are ammonia and air. So for the air inlet, which one is the rational one? Should we start from like the wanted temperature, like 200 degrees Celsius, or we take from atmosphere, which is around 27, and then kita heatkan dia?
Sekarang ni macam mana you nak start dengan 200 out of nothing? You guna blower kan you kena heat up lah.
So
sebab you guna air kan?
Yeah.
Mana you nak dapat air tiba-tiba 200 degree Celsius?
Okay.
Tak sekejap, itu nak masuk dalam reaktor ya Max?
That one need to mix with the ammonia, then only masuk dalam reaktor.
Oh, so preheat reaktor tu operating condition dia berapa?
At 90 degrees Celsius and around 0.7.
Apa? Berapa?
MPa. 7 bar.
Berapa degree Celsius?
At 190.
Oh, 890. So kira this is an exo process
Exothermic, yeah.
So you preheat lah kepada 200 degree C tu dulu.
Yeah.
It is preheated. Tak, you kena guna steam lah naikkan.
Okay. Tapi yang ambil tu from 27 like atmospheric.
Because dia atmospheric pressure. Dia memang blower, it's a blower, dia blow je masuk dalam. You cannot buy air anyway. Dia blow je. Dalam tu adalah filter sebelum tu, but you don't have to show it in your ICs.
Oh, no need filter lah.
Of course lah, tapi tak payah tunjuk. Maknanya you ambil tu daripada blower, air, lepas tu you blow, naik, you guna pressure berapa?
Pressure, atmospheric pressure kot, and then lepas tu kena compress.
Yelah, okay, tak payahlah guna heat, guna compressor terus. Compressor kan akan increasekan you punya temperature.
Oh, okay.
That's what I'm trying to say. You don't heat it, itu adalah the sequence the logical sequence of equipment. Jangan ambil air, lepas tu you heat it up, lepas tu you pergi compressor, temperature naik, lepas tu you guna cooler. Tak boleh, sebab you nak turunkan temperature kepada 890. Tak boleh lagi tu. Sebab compressor akan increasekan your temperature. So, you just guna terus compressor. Tengoklah berapa temperature yang dia dapat. Tapi kenapa nak guna 200? So mungkin compressor you, kalau you naikkan kepada, I don't know, daripada 1 bar, berapa operating pressure of your reactor?
Operating pressure around 7 bar.
You naikkan daripada I don't know 1 bar kepada 7 bar, mungkin temperature you naik shoot kepada 300. So terima je lah, tak payah nak guna 200 pun.
Okay.
Macam tu lah. Agak-agak je. Cantik kan?
Betul.
Okay, ada lagi apa-apa? Satu dah.
Lepas ni team production nitric acid boleh perform lah, doktor tolong banyak.
Apa dia? Apa dia?
Lepas ni team production nitric acid boleh perform lah, doktor tolong banyak.
Oh ya ke? Tak tentu juga.
Okay, madam.
Ada apa lagi selain nitric acid? Apa lagi?
Sorry?
Selain daripada nitric acid, production apa lagi?
Ada banyak, formaldehyde,
Propanol,
Oh,
Tadain.
senang ke?
I rasa senang yang lain tu. Nitric acid
Kalau korang bikin pilot plan tu ada je reference buku report lecturer sebelum ni, student sebelum ni ada dekat pilot plan.
Oh ya. Yeah. Oh yang tebal-tebal tu kan.
Yang ada yang atas rak tu dalam almari tu lah.
Juga.
Macam mana dah
masuk ATM.
kena kejar balik dengan Pak Gad. Dia tak lewat. Pilot plan pun kunci.
dah jadi crime lah kalau keluar sekarang.
Tapi I nak ingatkan you all ikut you punya senior punya design project careful. You tak tahu dia dapat apa. Tak dapat C. So careful.
Sebab bukannya macam mana dia orang punya tu tak. Dia orang cakap you reference tapi at the end tak ada pun.
So you boleh guna dia punya as a guideline je. Cari reference yang dia sebut reference tu apa. So then after that you can work with the guideline lah. Jangan ikut dia punya ini PFD ni you jangan, dia tak tahu sini you dapat apa. Dia kod lah masa design project 1 memang hancur lebur, kau kena kutuk dengan I masa buat masa marking, masa dengan presentation dengan industri pun tak betul kan, lepas tu proceed bawa design project 2, you never know. Be careful. Also kalau design project kat internet ke jangan. So you tengok reference tu boleh dan you evaluate. So the best thing to do it is that you cuba dulu dapatkan dia punya PFD dalam bentuk block diagram tu apa benda ke. You discuss dengan supervisor you lah whether okay ke tidak ke. Then after that you cuba HISIS. So that's the only way to go.
Betul. Block diagram first and then ISIS.
Kan masa you jumpa kat I guna PFD tu pun I tak layan you sangat kan?
Betul.
Sebab I cannot really tell lah. Maknanya my group jumpa I bagi tahu dia ada macam ni, lepas tu I kata okay you buat lah guna ISIS. Itu je jawapan simple I nak komen lebih-lebih pun tak tahu sebab tak tahu feasible ke tidak. Tapi cuma student I datang jumpa I lah bagi tahu ni memang pendek kan. Masa tu tak you bagi tahu you punya ni pendek kan?
Pendek.
You punya pelan-pelan tu pendek lah. Tak macam Dr. Fitra tengok student ni buat apa yang panjang tu.
Paling panjang buat ada 3 Oktober. Saya pernah buat 3 Oktober.
Tak ada apa grup yang satu lagi tu Amal? Dr. Fitra punya tu?
Sulfuric acid lah.
I rasa macam nak pengsan tengok dia punya proses flow dia panjang gila.
Memang banyak. Dia pun cakap.
Memang seksa lah. Memang seksa, sulfuric acid memang very high. Panjang lah dia punya projek. Tapi gitulah kena buat. So itulah you update you punya supervisor so that she's aware what's going on, you guna apa. But nothing much lah we can comment pun sampai she sudah dah settle dapat PFD then we can comment something lah apa yang tak kena. So itulah macam tab dengan group I ni biar kerja. Asalkan gancat ikut, dah PFD dah dapat, okay dah start kira, buat. Lepas tu kita check lah yang market and demand semua-semua tu where they are now, what should be ni. Tapi tu pun tak tertengok semua kot sebab masa tu first time guna ODM ni susah juga nak discuss kan tak kan? Tapi I think I did discuss with my design project much better compared to bila kita face to face. Bila face to face I macam itu buatlah ya Allah. Itulah.
So doktor, initial PFD tu macam just untuk dapat kita general overview of the process dulu je kan? Dia bukan finalize lagi tu kan?
Bukan. Sebab
So nanti after kita masuk IC semua and everything baru kita boleh finalize PFD.
Ya, correct. Sebab rasa yang kumpulan I dulu pun sikit je contact kan. Yelah pendek PFD-nya. Lepas tu bila kita buat IC dia jadi macam Atira punya group yang dia worry tu lah. Nampak macam sikit. Lepas tu boleh ke? Tapi kita go ahead je lah. Kita tak naklah tukar kepada new production. We don't want to go panic. So kita hadap je apa yang ada. Macam tu. So itulah in the end dia grow into something lah yang everybody ada task untuk design. Nobody is going to say anything kalau tak task buat tank. People will ask, mungkin tak the worst thing, kenapa you tak design absorber, you buat tank. Supervisor I kata dia tak nak gunakan je lah nama I tak kisah. Supervisor I dah bagi 2 heat exchanger, so we decided that no one should design some other thing pun, ada critical equipment, so design tank. Let's see what happen. Itu je lah. Kalau by the way, kalau macam something like a flash drum pun actually is a tank. Sebab you masukkan pressure berapa, dia akan jadi flash, dia tak nothing inside pun. Dalam flash drum is only a cylindrical, cuma also dia ada heater, kalau dia ada heater. And then dia ada what we call as apa benda kat atas tu, ada macam a kind of padding sikit supaya whatever yang sebelum dia keluar, dia macam filter tau. Supaya yang liquid phase tu dia tak, macam nak cakap bubble, dia macam bubbling tu dia tak akan lepas daripada pad tu lah, padding tu. So maknanya yang dekat vapor outlet tu is only vapor. So whatever dalam bentuk droplets akan condense back because dia dah terkena dengan that pad tu yang dekat dalam flash drum. So basically flash drum punya principle dengan tank yang macam Tek buat ni is the same thing. Cuma yang Tek buat tak ada pad tu je lah, pad tu simple je. So okay pada I. Not to worry.
Kalau untuk design tank tu doktor, kita kira area macam biasa je lah. Kalau macam flash drum tu kan dia guna apa nama gas, velocity of gas kan. So kalau macam tank guna area biasa je lah kan.
Sama lah, you have to consider the velocity of gas juga kan.
Oh, even ada sikit still kena guna lah.
Ada gas ke masuk, semua liquid kan?
Semua aqueous bukan liquid. Masalah.
Semua aqueous tak ada gas kan? Tapi prinsipnya sama, but then you have to keep the temperature tu supaya nothing is evaporated. Kalau tidak you will lose your acid lah, HCl you.
Sebab dia gas velocity tu pun dia akan kira yang output punya stream.
Okay. So cuma sekarang ni you fokuskan dengan the type of heating element you tu. You have to decide. Benda tu banyak juga. It's like you are designing a heat exchanger pula because you need to calculate the heating element yang you want to keep the temperature to that. You have to decide on the fluid, on the refrigerant. You see, because kalau the temperature increases then you have vapor. Nanti you loss of your HCl lah.
Dia punya emosi lah, kena ambil kira.
Yeah, it is not simple, it is complicated. Okay lah. Lagi? Ada soalan? Tak ada dah?
Dia orang pandai kita boleh buat ni.
Apa Afiq?
Untuk kalau ada filter tu,
macam
kalau proses tu macam ada filter
kat mana?
Like platinum filter right after conversion punya reactor tu, yang kena masukkan dalam ICs.
Filter tu untuk apa?
Sure, dia untuk
tak dengar lah Afiq, tak dengar.
Dia untuk impurities kot. So tak payah.
Purity?
Impurity.
Sekejap. You produce precipitation ke?
Sorry?
You produce ada solid ke?
Tak ada.
Kenapa nak guna filter?
Ya tu sebab dia tulis kat situ platinum filter right after conversion. Tak tahu.
That's why you kena guna high seas. Tengok apa jadi. Kalau dia hanya liquid dengan vapor, you langgar je.
Okay.
Itulah takut macam ada precipitation ke? Benda tu gas, reaction dalam bentuk gas
Gas.
Yeah, betul.
Gas. Vapor.
Sebab you guna air ke?
Betul. Air.
Dia nak bagi clean code project. Kenapa dia tak filter sebelum masuk dekat dalam reactor?
Sebelum masuk pun dia filter air tu. And
I
then
see.
right after conversion pun dia filter juga guna platinum filter.
Tak payah. Itu untuk ISIS tak payah masuk.
Okay.
Sebab kita assume air tu without any dust. Macam katalah you buat kat Malaysia kan. Dengan penuh dengan habuk lah, tiba-tiba ada pembakaran lah, apa benda.
Tidak considering
jadi haze lah, apalah. So they want it to be clean process as opposed to that's why they nak filter in, filter out untuk dapatkan the maknanya purity you berkurang lah untuk you punya macam mana nak cakap you can you avoid the impurity in your product. Jadinya they have to install a filter. So those yang design reactor kena include benda tu later on semester 8. So but dalam HISIS I rasa tak perlu.
Okay.
Kan tak kan? Rasa
tak kot.
Tak. Dia tidak akan mengubah apa-apa pun sebab you tak ada, you letak air tu nitrogen dengan oksigen je.
Sebab macam before ni pun kalau ikut kita orang punya reference, kita orang punya reactor furnace guna air, guna fuel, so tak ada guna filter apa pun. Dia terus je direct masuk reactor.
Okay, we don't need it. Okay, so grab this time lah to skill HISIS ni. Siapa yang buat HISIS ni memang amat berguna lah. So maksudnya bila you cari kerja nanti dalam resume you letak skill you apa? HISIS. Student I ada 2 orang dapat kerja, setahu I lah, ada ramai lagi yang dapat kerja because of dia punya skill dalam HISIS. Sebab company tu memang guna HISIS dan company tu is a consultation firm. Okay. Tak ada apa-apa lagi? Tak ada soalan Yang lain nak butan diol tu rasa straight je, liquid. Simple rasa. Supervisor, coordinator you pun dah tak ada tajuk dah ni, dah main recycle tajuk dah. Okay you guys, if that's the case, so thank you very much Ted and Amal for being here. Tepuk tangan sikit.
Baik Amal.
Thank you very much. Tergulak lah pada everybody. So I'm sure I akan kena mark some of your work lah. So gitulah. So I dah share tu, ikutlah apa. So that rubric tu sebenarnya I dah share dekat Moodle, so you can have a look at it. So tengoklah. Gitulah, tak ada benda pun. Itu je pun I tengok pun. Okay, if that's the case, thank you very much, and especially kepada Ted dengan Amal yang duduk kat sini. Spending
Thank you guys.
Thank you very much. And all of you, good luck, all the best. This is his final class. Jangan lupa isi attendance. I still have to report your attendance to TDA. And even though this is audit course, tak bawa satu markah pun dekat you punya final. Tapi I hope this is very helpful lah for your design project.
Dia bawa soft skill.
Ya. Gitulah cerita sebab bukan dengan you all semasa lepas. Okay, rajin-rajin lah cuba exercises yang dah ada tu and see what happen. But I'm sure you will learn through me. That is learning it also, that you guys don't worry lah. Okay, if that's the case, thank you very much all.
Okay, thank you Doctor.
Thank you Doctor.
Okay,
Thank you, Doctor.
Thank you.